Hello guys, today we are going to start our series in Calculus 2 and the first topic will be improper integrals. So I'm going to introduce you to the improper integrals. We're going to know the definition of the proper integrals and how we can integrate the proper integrals. Now, an improper integrals is an integral whose upper or lower limits goes to infinity or have infinite discontinuity on a certain interval. Let's suppose we have got an integral if fx is an integral with a and b limits. So if it is improper, this actually means two things. Number one, it has an infinite upper or lower limit. It's either a goes to negative or positive infinity or b goes to negative or positive infinity. That makes it an improper integral. Number two, if it has an infinite discontinuity, so an infinite discontinuity on an interval that is probably interval a and b. So if there is a certain kind of discontinuity within the function that we are integrating, that makes it an improper integral. One of the example, if it has a vertical asymptote or horizontal asymptote. So we're gonna see examples of the improper integrals. So some of the examples are maybe if you have got an integral from 2 up to infinity of 1 over x dx. This one is improper integral because its upper limit goes to infinity. If you have let's suppose an integral negative infinity to 0 of e power 2x dx, this is as well improper integral. So we might have different improper integrals. So let's suppose in the case we have got an integral from 3 to 5 of 1 over x minus 3. This is an improper integral. Why? Because we know that for the function, suppose if we have a function fx is equal to 1 over x minus 3, we know that there is a discontinuity at x is equal to 3, because we know that the denominator x minus 3 must not be equal to 0. So there is discontinuity at x is equal to 3. So since we have got a discontinuity at x is equal to 3, that is an improper integral. Now, let's deal with some theorems which are very, very, very crucial, and we are going to be using them more oftenly. So the first theory that you have to know, that is actually theory number 1. So theory 1. So if we have an integral from negative infinity to c of fx, and the same integral but different limits, forgot dx here, if both are convergent, if both are convergent, then from negative infinity to infinity of the integral fx dx is equal to negative infinity to c fx dx plus an integral from c to infinity fx dx. Now, this appears too long and actually too complicated, but I'm going to explain the key words. I'm going to try to break it down so that you can actually understand what's going on. So we have two integrals, and all of them, they are improper. So we have got the first integral have got a lower limit of negative infinity, and the second integral have got upper limit of infinity. So they are improper integrals. So if both are convergent, so what do we mean by convergent? An integral is convergent if, when evaluated, it gives a real number. It does not give infinite number. It does not give negative infinity or positive infinity. So if fx, let's suppose a to b, is equal to a number c, it gives a number c whereby c is not positive or negative infinity, then the integral is convergent. In other words, the integral is convergent if it gives a real number, negative or positive number, just a number, it's convergent. If it does not, if the integral results into positive or negative infinity, or it gives infinity, that integral is what is known as divergent. So if the two integrals, the two parts of the same integral, that is the integral from negative infinity to infinity, which can be split into negative from the integral from negative infinity to c and from c to infinity. Actually, if these two integrals are convergent, which means if both are convergent, it means that the integral is convergent as well. The integral negative infinity to infinity. These are two important things that you have to know. Now, so in we have seen that if the integral, now actually splitting the integral, like let me give you a good example so that maybe you can get a clear picture of what I'm talking about. If you have maybe just a simple integral from 2 up to 5 of x dx, this integral, if we want to solve it normally, we know that it's going to be x squared over 2 evaluated from 2 to 5. So if we do some maths here, we'll have 5 squared over 2 minus 2 squared over 2, which is equal to 25 over 2 minus 4 over 2. And the answer is going to be basically 21 over 2, or which is 13.5. This integral can be split into 2. In other words, we can actually use split it into different limits. For example, you can go from 2 to 3, then from 3 to 5. So it's the same integral, and when we integrate, we find the same result. So actually, if you have got, let's prove it. 2 to 5x dx is the same as an integral from 2 to 3 x dx plus an integral from 3 to 5 x dx. Remember that we are moving from 2 then to 3, then from 3 to 5. So we can actually split it in many ways, in different ways. You can actually split it. We can even go from 2 to 3, from 3 to 4, from 4 to 5. So it can be longer. So as you can see now here, the first integral, if we integrate this one, so it's the same result but different. So I'm gonna do this quickly. So here we are having x squared. We're going to use this function. So here we're going to have x 3 which means 3 squared over 2 minus 2 squared over 2, and here plus we have which is 5 squared over 2 minus 3 squared over 2. Simple. Let's add all, because we have the same denominator, then we can add, because we have the same denominator, then we can add the upper numbers and maintain a denominator. So which means we have 9 minus 4, that is 5, then 5 plus 5, that is what 5 plus 25, that is 30. 30 minus 9, that is 21. So which means the answer is 21 over 2. So as you can see, that is basically the same the idea behind splitting and improper integrals, and by introducing a constant, like a number c, in order to actually to determine whether the integral is convergent or divergent. So let us now go back to the idea. So we have an integral from negative infinity to infinity, fx dx. This can be split. We can go from negative infinity then to c, then we can go from c then to infinity. So this can be split into from negative infinity to c fx dx plus, and then from c to infinity, which means fx dx. So that is that. So what is the theorem number? So if here I've got the first integral and the second integral, if these two integrals are convergent, meaning that if they all result into a real number, which means they are actually, which means the whole integral, this one, negative infinity to infinity, is convergent. If either one of them is divergent, it means the whole integral is convergent, which means if from negative infinity to c fx dx is convergent, and c to infinity fx dx, if these two are convergent, it means that the integral negative infinity to infinity fx dx is convergent. If either one of them is not convergent, if it does not result into a real number, that means that the integral is not convergent. So keep that in mind. Let us see an example. So let's suppose we have an integral 1 up to infinity 1 over x squared. So how can we solve this how can we integrate this improper integral? What we have to do, because we cannot actually integrate an infinity values directly, we have to introduce a parameter t such that the t represents an infinity and it goes to infinity. So it means we have to use the idea of limits. So actually, this is the same as limits as t goes to infinity. Let me write it very good. As t goes to infinity of an integral from 1. So where there is an infinity, we replace it with t. It means we have to put t here. 1 over x squared dx. I think that is very clear. So actually, this t is actually a parameter which goes to infinity. So we can actually now solve and find the limit. Okay. Now let us integrate. So this is the same as limit as t approaches infinity. The integral of 1 over x squared is the same as let me put here negative 1 over x, and it goes from 1 to t. Also, the basic formula, if you have any number like x1 over xn such that n is not equal to 1, to integrate this further, we can use the formula which is just the same as 1 over xn minus 1 multiplied by n minus 1. So it's the formula that the quick formula that I can use. So which means you have to subtract the power by 1 and you put the same number in front. So I think that makes sense. So in the case of 1 over x squared, so we have actually, yeah, which means here it has to be, so here there's a typo. Which means it has to be 1, which means it have to be 1 over x. N minus 1, just as usual. And then here, you're going to do the opposite, which means the coefficient will be the opposite of this, which means to be negative. So here you're going to have actually negative n minus 1. For example, an integral of 1 over x3, we know that it's going to be x negative 3. So x negative 3, then we have that 1 here, and we have to divide by 2 by negative 2. So if we use we apply the sum function to 1 over x squared and then divide by negative 2. Yeah, that's pretty clear. So, or if the formula is somewhat complicated for you, you can just use the normal integration. I hope at this point you know how to integrate. So we can now solve, we can actually find the limits and evaluate and find the limits. So here it's gonna be limit as t approaches infinity. So here we put t, it's actually 1 negative 1 over t minus 1. Remember that here we replace by 1 minus 1. This means minus 1 over 1, which means 1 over 1 just 1. So here you're going to have limit as t approaches infinity of this one of the function 1 over t plus 1. Now, just evaluate the limit. We know that this, we know that 1 over x, limit 1 over x as x approaches infinity, this is gonna be 1 over infinity, which is equal to 0 actually. So whenever you divide by infinity, negative or positive infinity of the rational function, that means the limit goes to infinity. So that is the basic thing that I have to know. So for example, limit as x approaches infinity of 1 over 2x. So if you put infinity here, this is going to be equal to 0. So it means the limit is going to be equal to 0. So here, the limit is going to be equal to, here we take the limit of every term. So it means you have the limit of t to infinity of negative 1 over t plus the limit as t approaches to infinity of 1. So this is going to be 0. Then this one, because the limit of a constant is just a constant, which means 1. So which means the answer is 1. Yeah, I hope that is very, very clear. Now, let's introduce theorem number 2. So we have seen that in the previous example, we have seen that the integral from 1 to infinity of 1 over x squared is equal to 1, which means it is convergent because we are getting the same, we are getting the real number, we get to 1. We do not get infinite number. Okay, we do not get a positive or negative infinity, which means this one is convergent. So there is a theorem that we use to determine whether an integral is convergent or divergent. So if an integral from a to infinity is 1 over x raised to power p, and you know a is greater than 0, that's very, very important. So if p, so we have two cases here. Let me highlight that because it's very crucial, because we're gonna use it throughout the calculus 2 course. If p is greater than 1, which means this integral is convergent, which means wherever we have a p greater than 1, the integral is convergent, which means this results into convergent integral. And if p is less than or equal Very, very important, is less than or equal to 1, the integral is divergent, which means it's residing to negative infinity or positive infinity, which means it's divergent. Its value does not give a real number. It gives infinity. Now, let us see examples. So, for example, if you have an integral from 1 to infinity, and then have got 1 over x squared. This is the same question that we solved. We found that this resulted into 1, so which means the answer is just 1, which means this is divergent. If we put here 1, because if let's suppose p is less than 1 or equal to 1. So if we put from 1 to infinity and then 1 over x dx, we know that if we try to evaluate the integral, we find that it's equivalent to limit as t approaches to infinity, then integral of 1 to t 1 over x dx. So we know that an integral of 1 over x is it's natural logarithm of x, which means it's ln x. So we have limit as t approaches infinity is going to be ln x evaluated from 1 to t. So this gives us limit as t approaches infinity ln t minus ln 1. Actually, the logarithm, any logarithm of 1 is 0. Yeah, I hope that clear. Logarithm of 1 is 0. So we have got at the end we have limit, because this is 0. So we just take this, which means limit as t approaches infinity ln t. Now let's see the function, the logarithmic function. So if you have, so these are very crucial, so you have to remember this is tough, they are very important. So how does the logarithm function look like? So basically ln x, so the function, let's suppose fx is equal to ln x, the function of fx is equal to ln x. So here if we have 1, we know that if x is equal to 1, then y is equal to 0. So basically, and then we know that x cannot be equal, cannot be equal to 0. So the function goes like this. Which means goes like this. So it will not actually touches the y-axis. So we see the limit as t approaches infinity, which means let's suppose this is x is t, which means here as t approaches infinity, which means t is going this way. So as t approaches infinity, we see that the limit will be positive infinity, which means this gives infinity, which means the integral is divergent. Pretty clear. Which is a very, very important. Now, theorem. So, another case is when we have a function. If we have an integral from 1 up to 1 of the we have an integral of 1 over x to the power p of the limits 0 and 1. If the limits are 0 and 1, then if p is less than 1, which means this converges, this integral is going to converge. If p is greater than, which means this is opposite to theorem number 2. So this is actually opposite of what we have just seen. So wherever I have got limits from 0 to 1, which means the the integral converges when p is less than 1, and that integral diverges when p is greater than or equal to 1, which means it diverges. Let's give an example. So if you have got integral from 0 up to 1 of root x dx, this one gives number 2. Gives 2, which means this one is convergent. Okay. And let us prove it. Let us try to solve it. So let us try to evaluate an integral from 0 to 1 of 1 root x. So it's good that you have a pen and the paper so that you can actually try to do it. You can pause the video and try to do it on your own. Okay, that is the answer, but let's try to prove it. Let's try to evaluate it. Okay, actually this is this integral. I'm going to introduce the discontinuous integrand in the next series. Okay, so actually this is the same as, so here is the same as limit as t approaches 0, because here we have got actually a function. Suppose we have got a function from 0 up to 1. So because when we approach 0, 0 is actually discontinuous, because 1 over root x, if this is a function, which means x must not be equal to 0, because 1 over 0 or any number over 0 doesn't make sense. So x must not be equal to 0. So that's why we are going to take a limit. We're going to introduce a parameter t and take a limit as we approach a 0 from the right. Okay, so this becomes one-sided limit. So limit as t approaches 0 from the right of an integral where there is 0 put t to 1 of 1 root x dx. This is going very interesting. Now, try to evaluate the limit. If we evaluate the limit, if we integrate, we know that actually the integral from t to 1 over root x dx, we know basically root x is the same as x power 1 over 2. So here I've got 1 over x power 1 over 2 is the same as x negative 1 over 2. The basic idea is that we have, this is the simple, the rule of logarithms, you know already. So we can actually find, we can actually take this one from t to 1 x negative 1 over 2 dx. So this is gonna be x negative 1 over 2 plus 1 over negative 1 over 2 plus 1. So this would result into x, which means 1 minus 1 over 2, that is 1 over 2, which means that is root of x over 1 over 2. Yeah. And we can try to remove, we can multiply 2 on both sides to simplify the complex fraction. So we're going to have 2 root x. So 2 root x evaluated from t to 1. So this is going to be 2 root 1 minus 2 root t, which means the answer is 2 minus 2 root t. Okay, yeah. So here we can, so here it's a limit as t approaches 0 from positive, from right, two minus 2 root 2. So we can factor out the 2, which means it's going to be 2 limit as t approaches 0 from right, which means 1 minus root 2. Okay, so here limit of, here it's each and every term here is going to have a limit on its own. So limit of 1 as t approaches 0, which means it's just 1. And here limit of oh, I'm sorry, here there is t, it's t here, limit as t approaches 0. So let's see how the function looks like, which means if you have got a function root of x, it looks like this, it goes like this. Okay, that's root of x. So when this approaches 0 from the right, which means if it goes like this, if it approaches 0 from, let me highlight that because it's very important. If it approaches 0, okay, if it approaches 0 from the right, as you can see, we get we get 0, which means here the limit here is 0 minus 0, which means this is minus, which means here it's 1, which means here we have 1, which means the limit here is going to be 2 times 1, which is equal to 2. Which means the answer is actually 2. Because the limit of root t as t approaches to 0 from the positive side, from the right, which means it's 0. And the limit of t and the limit of 1 as t approaches 0 from the positive is 1. Actually, the limit of a constant is just a constant, which means here this is going to be 2 times 1 minus 0, which is 2 times 1, which is equal to 2. Yeah. I'm going to explain more on discontinuous integrand. So in the next series, but that is what you're supposed to know. Now, in the next series, we are going to solve numerous examples, but as of now, let's just summarize what we have discussed in this tutorial. So we have seen that an integral, if you have got an integral, let's do summary, fx is improper if either limits, which means upper or lower, are infinite, which means if you have got either positive or negative infinity. And number 2, if there is a what? There is discontinuous. So if there is a discontinuous, that is in the case of a rational function. If there is a discontinuous anywhere, if there is a breakdown of the function anywhere, which means that result into improper integral. Okay, that's the first thing. So another important point worth mentioning, we have seen that the limit can actually be split just the way you can the improper integral can actually be split just the way you can split any other integral. So if you have got an integral from negative infinity to infinity of fx dx, we can actually use any number, any constant. This can be split from negative infinity to c fx dx plus c to infinity fx dx. That's very important. And this integral will be convergent if these two are convergent. So whenever, which means if these two integrals which have been split from the main integral, negative infinity to infinity, are both convergent, which means the integral is convergent. So if either one of them is convergent, which means the integral is, if either one of the split integrals are divergent, is divergent, which means the integral is divergent. If both or either one is divergent, which means the integral is divergent. Which means for this integral to be convergent, these two integrals have to be convergent, all of them, both. And if either one is divergent, which means the integral is not convergent, which means it's divergent. Now, we have seen the test of divergence or convergence. When you are given when you're given an integrals of the form from a to infinity 1 over x to p, which means if p is greater than 1, which means here we have to remember always that a is greater than 0. So if the power is greater than 1, which means this results into convergence, which means the integral is convergent. And if p is less than or equal to 1, the integral is divergent. We also saw the integrals from the integral of the limit 0 and 1, which means if you have got the integral in the form of 0, the limit of from 0 to 1 of 1 over x p, this one dx, I'm forgetting dx, I don't know why. So if this one, if p is less than 1, which means this is convergent. Actually, it is the quite opposite of the first test. And if p is greater than or equal to 1, the integral is divergent. So that is what we have discussed. So it's very, very, very important, and this forms a critical foundation on understanding the improper integrals. So in the next tutorial, we're going to see how can you can solve different examples given different limits of integration. Gonna see the techniques that are gonna be employed to evaluate improper integrals. Yeah, thank you very much. Have a good day.